Today, very experienced and the knowledgeable faculty, Professor Prabal Chaudhary from Baba Atomic Research Center. It is a great privilege, sir. You are with us. You have accepted our request. We are thankful to you, sir. And
Thank
as
you.
today, thank you very much, sir. As today we are having very important topic related with the radiation metrology. As we are all aware, radiation plays a very important part in the human's life nowadays. As we are using 1G, 2G, 3G, 4G, 5G, and all type of Gs now, because all today we are all Gs. We are working with a G only. Secondly, these radiation is also playing a very important role for the food industry. As with the help of this radiation technology, we can also increase the lifetime of a perishable food product, maybe an onion, maybe potatoes, maybe food out of maybe these fruits, etc. So as today we have Professor Prabal Chaudhary, I am not taking more time. He will explain us what are the new things in the radiation metrology we are doing and how the industry can take the help of our renowned and one of the most important center, Baba Atomic Research Center in India. As Professor, I would like to introduce Professor Chaudhary. He joined Baba Atomic Research Center in 1994, long back after this BARC training school. As we are all aware, this is 1 year course and it actually creates the radiation technologists and the scientists in the field of radiation. He has carried out design and development of various radiation monitoring systems like aerial gamma spectrometry system, quad rotor based aerial radiation monitoring system, and design support tools or nuclear and radiological emergencies. He has carried out planning and execution of several aerial radiation monitoring exercise jointly with defense forces. Shri Prabal Chaudhary has contributed significantly towards the development of 25 DAE radiation emergency response centers, Department of Atomic Energy, across the country. Currently, he is heading Radiation Safety Systems Division of Baba Atomic Research Center and carrying out activities towards preparedness and response to nuclear and radiological emergencies and radiological impact assessment. Sir, thank you very much for accepting our request, and I hope that today's lecture will be one of the best lectures of this series, which we are continuing since last many years. And every Saturday, sir, we have this lecture. I think I had already add you, or otherwise I will add you in our group of experts who are the scientists or the technologists of the country. Thank you very much, sir. Over to you, sir. After this presentation, sir, this video we will place in on our YouTube channel, Legal Metrology YouTube channel, and your presentation we will also share with all the participants to understand better if they wish after the program. Please, with your kind permission, sir.
Thank you, Agarwal ji, for kind introduction and giving me an opportunity to be a part of this webinar. I have been attending few of your seminars earlier. So without losing much time, let me start with my presentation.
Please, sir, please.
One moment. Is the presentation visible?
Yes, sir, it is visible.
Okay, first of all, welcome all of you to this webinar. So mainly radiation metrology, but we will be mainly covering the ionizing radiation metrology. So this is what I wanted to make clear before the presentation starts. So basically, to just have a brush up of metrology, so everyone is aware, metrology is a science of measurement and its applications, and it establishes a common understanding of units. So we have various units, various measurements, so we need to have a common understanding. And then the definitions or the units of measurements, all the definitions what are used in the measurement, they are defined, very well defined. And this realization of these units in measurement practices, when we are carrying out any measurements, we will be using these units. And the traceability is one of the important aspect which links the measurement to the reference standards. For any measurements, we all know that there must be a reference standard, and then for anyone carrying out measurements has to be traceable to the reference standards. So as a metrology, it is our responsibility to provide that traceability. So we'll look into the presentation and come to know what to be done. And BIPM says that metrology is the science of measurement, embracing both experimental and theoretical determinations at any level of uncertainty in any field of science and technology. So there are various subfields of metrology, as this particular this seminar, that web series is being conducted by legal metrology. That is one of the most important aspects of metrology. Then we have scientific metrology, in which we have the, as I mentioned earlier, establishment of units and measurements, and then development of new measurement methods. Any quantity to be measured, the new method has to be evolved, or it has to be carried out scientifically. And then realization of measurement of standards, and then transfer of traceability standards to the users. And coming to the industrial metrology, applications of measurement to manufacture and other processes, ensuring suitability of measurement instruments, and calibration and quality control are one of the aspects. So this slide makes us a very clear definition. All of us knows what is radiation. That is an energy. Basically, radiation is nothing but an energy. And then these are termed in two parts. One is ionizing radiation as well as non-ionizing radiation. And if you see the spectrum, electromagnetic spectrum, so it is clearly defined, like the radio wave, the mobile waves, all this comes under the part of non-ionizing radiation, whereas the gamma rays, X-rays, which are having higher energies, neutrons, alpha and beta particles, they are ionizing radiation. So we'll be mainly dealing with the ionizing radiations and then the metrology for that. And just to give an overview, all of us is living with radiation. So ionizing radiation, we cannot escape from ionizing radiation. And definitely radiation is a natural phenomena, and it is available in many forms. And definitely it's very good for our well-being as well as the health. This reason being, if we go anywhere, so we'll be always exposed to natural radiation, and the levels of radiation may be different, like cosmic radiations. And when we travel in air, we get radiation which is around some 20-30 times higher than what we get in the ground. But all those limits are quite safe, and then it's well accepted. And then another source is from terrestrial. We have lots of radionuclides present in the Earth's crust, which is formed during the formation. And these radiations keep on giving us radiation all the time. And if we can see that some of the areas in our sea beaches where we have higher radiation levels, which are attributed to the monazites with high quantity of thorium. And then radon is one of the natural radiation, ionizing radiation, which is available from the decay of the uranium in soil. And of course, internally, we all are radioactive. We all emit around 5,000 photons per second. This is what was the radioactivity we have in our body. Like the bones, the potassium content in the bones, they are radioactive. As well as there are lots of foods which has inherent radioactivity, like banana is one of the food which we intake regularly. They have potassium in it, and these are my main idea is to say that we are always living with natural radiation, ionizing radiation. And for the benefit of the mankind, there are man-made sources of ionizing radiation. So all of you know that we have lots of applications in the medical health and healthcare. So we all are benefited by the radiation technology, both in terms of diagnostic and therapeutic. A diagnostic to find out any sort of problems in the body. The radioactive element is injected in the body. They are short-lived, and they go to the part of the body, and then we can carry out the gamma imaging to find out exactly, locate which organs are affected. These are well used. And then for therapeutic use, of course, you must be knowing the cancer treatment by using cobalt-60 sources. So the cancerous cells are being killed by giving a radiation at the accurate locations after finding out. And similarly, there is an iodine treatment which is given to the patient who is having problems with iodine. So radioactive iodine 131, that is one of the radionuclide which is given to the patient, and that radioiodine exactly it has the affinity to get settled in the thyroids, and then thyroids they will be giving the dose to that affected cells, and then is being cured. And of course, in nuclear activities, we have the nuclear fuel cycle where we starting from mining and milling, then fuel fabrication, then in the nuclear power plants, and then reprocessing. This is a full complete fuel cycle where radiation is effectively used, mainly for the power generation. And then we have lots of societal benefits also. We are able to produce different types of radionuclides like uh, cesium 137 is one of the product which is we call it as uh, wealth from waste, basically reprocessing that cesium pencils. They're used for blood irradiators. So with that irradiation of blood, we can make it more blood free from any infections. And of course, the nuclear test which have been carried out earlier, so they have fallouts of ionizing radiations, and some activities may come through the radiological accidents or threats. So for this, we have enough emergency preparedness and response system in our country to deal with all these radiation emergencies. Then coming to industrial applications, we have industrial radiography, where we can detect any defects in the uh, some of the products when you want to find minor defects like welding joints and other devices. And then we have nucleonic gauges, with which we can measure the level of liquids or any other uh, oil. Generally, oil industries it is used where it's very difficult to find out the levels, and it is a non-invasive method. So you have a source on one side and the detectors on the other side. By the level of finding the attenuation level, we can find out what is the level of the liquid. So these are the industrial applications, and some more industrial applications. There is one of the tracer experiment in which in the pipe flowing liquid you can inject radioactivity, and wherever there may be minor leakages, so we'll have a concentration of radionuclides there, and then through monitoring the entire length of the pipe, we can find out which are the areas affected, and then the corrective measures can be taken. So what I mean to say is in lots of industrial applications, radiation sources are used and transported all over the country and all over the world. And of course, in the applications of food and agriculture, we have very huge applications. I'll give a simple example of mangoes. So we have irradiation of mangoes. Mainly, it's required for export to many of the countries which expect the mangoes to be free from uh, any insects or any probable insect this one. So we have to have uh, gamma radiation irradiate the mangoes, and it can be transported. And then of course, to increase the shelf life, like onions and potatoes, they we have irradiators where we expose to gamma radiation to all this, and then increase the shelf life, will inhibit the sproutation process. And I would like to make very clear in this point that while irradiation, we are giving a gamma dose to the like onions and potatoes, but there is no radioactivity as such present in that. So it's quite safe for consumption. The only the gamma rays are given to kill the cells which promote the sprouting. Then also in spices and other some of the lentils, we see that insects are, if we keep it in shelf, we get lots of insects. So these through irradiation, this process can be cleared, so we can enhance the shelf life. And of course, we have our borders where our soldiers they need the food, packaged food, which have to have shelf life, extends the shelf life. So for that also lots of applications have been carried out. And coming to agriculture, so that nuclear and agriculture uh, division of BARC, they are creating a mutation in the uh, grains, and then which is producing higher yields. So this is also a very good application of nuclear application in the agriculture. And of course, in research, lots of researchers are using radiation for calculation of shielding as well as the properties of material and other aspects. Coming to radiation metrology, we have defined a few of the quantities, which are one of them is the fluence. The fluence, which is a number of particles, maybe it may be neutron particles or this in per unit area. So that is the fluence. And then an exposure. As I mentioned, now we have always exposed to radiation. So how much ions are produced, because this is an ionizing radiation. Ionizing means that you are you are able to remove one electron, at least one electron from an atom, which produces ions. Then main quantity in the radiation metrology is the absorbed dose, that is energy per unit mass. How much energy you have absorbed, that is defined in terms of gray. So 1 gray is 1 joule per kg. 1 joule of energy deposited in 1 kg of mass is gray. That is a very fundamental basic unit of gray. And then we have equivalent dose, so which is meant by radiation weighted absorbed dose. This is required because the gamma, alpha, and beta, they have different weightage factors, weighing factors. So if we for all those quantities, weighting factors are available. So once absorbed dose is multiplied by the radiation weightage factor, we get the equivalent dose, that is sievert. For example, gamma is having a weightage factor of 1. That means 1 gray is equivalent to 1 sievert equivalent dose in terms of gamma. Whereas if it is a neutron, and neutron also of course depends on different energies, higher energy neutrons, what we call is as fast neutrons, they have weighting factor as 20. So to get equivalent dose for neutron, we have to multiply that 1 by 20. So it comes as a 20 sievert. So I hope I could make this point clear. And then we have another quantity, which is effective dose, which is again specific to the organs. Different organs behave in different way. If the radiation is going to a particular organ, they have different tissue weightage factors. For example, all the organs tissue weightage factors are defined. So first we have absorbed dose, that is the basic mass per unit, energy absorbed per unit mass. Then if we multiply it by radiation weightage factor, we get the equivalent dose. And then when that equivalent dose is multiplied by the tissue weightage factor, we get exactly what is the effective dose, that is what is the dose effect of that dose in that particular tissue. Then of course we have other quantities, which is kinetic energy related per unit mass of matter, and then a dose equivalent. Dose equivalent is operational quantities for estimation of effective and equivalent dose, that is used in personal, ambient, or as well as in directional. Coming to the global metrology system of ionizing radiation, this figure may not be very clearly visible in a very smaller screen. So we have a treaty of the Meter Convention, which was established in way back in 20th May 1875. That is also celebrated as the World Metrology Day, and this year also will be celebrating this on 20th. Then we have a general conference of weights and measures, that is CGPM. That is a diplomatic. This in diplomatic level we have these two things. Then International Committee for Weights and Measures, so CIPM, and then under CIPM we have several consultative committees. So the consultative committees which is related to ionizing radiation is CCRI, a consultative committee for ionizing radiation. So under that consultative committee, we have again different working groups. So I'll mention about the different working groups of CCRI. in the subsequent slides. Then we have BIPM and then Joint Committee for of the RMOs and the BIPM, the JCRB. And under JCRB, we have regional metrology organizations. So we are mainly affiliated with APMP, that's Asia Specific Metrology Program. And under APMP, we have the TCRIs, that is Technical Committee of Ionizing Radiation. These are defined by the CCRI. So ionizing radiation falls into TCRI. And in TCRI, we have the designated institute. So BARC is the designated institute for ionizing radiation metrology. And we have CSRI, NPL, India as the NMI for the country for all the other measurements, whereas for ionizing radiation, and we are the designated institute. And for all the measurements which is carried out for ionizing radiation, we do have conventional instruments like electrometer and then volume and other equipments. All these equipments are traceable to our CSIR and NMI, it's NPL Delhi. So we calibrate our all auxiliary instruments which are not from for ionizing radiation, that is with NPL. Then to give us some brief description of CCRI, this Consultative Committee for Ionizing Radiation. The mission is to discuss, foster, enable, and coordinate the development, comparison, and promulgation of national measurement standards for ionizing radiation. So CCRI is particularly the mission is for meant for the ionizing radiation metrology, and it enables all the users of ionizing radiation to make measurements with confidence at an accuracy that is fit for purpose. And the vision is a world in which the many benefits of ionizing radiation for healthcare and technology can be realized by accurate, scientifically rigorous measurement, confident that the associated risks are constrained. So basically, the CCRI has got 3 sections, and all our activities towards ionizing radiation metrology falls under these 3 categories. CCRI 1, that is for X-ray and gamma rays and charged particles, and CCRI 2 is measurement of radionuclides, and the third one is specifically for neutron measurements. Then CCRI are having different working groups. So communication working groups, so where they are communicating how to communicate each other. And then CCRI section 1 is a key chairpersons working group that comes under section 1. And then radionuclide therapy and quantitative imaging working group, and brachytherapy standards working group, and we have a group on digital transformation, then key comparison working groups, which looks after the key comparison database of the different quantities, then group for radioactive sources and alternative technologies. The alternative technologies means that we have some of the radiation technology applications. We use alternate technologies like linear accelerators and proton accelerators. So that comes under this particular group. And there is an ad hoc group, working group on strategy. Coming to APMP ionizing radiation, there's a TCRI, that is Technical Committee for Ionizing Radiation, that is in line with the CCRI CIPM, that is dosimetry, radioactivity, and neutron measurements. The TCRI coordinates the regional comparison in our Asia Pacific region of measurement standards, and these comparisons establish the equivalence of radiation measurements within APMP. So we are also part of APMP. We carry out comparisons of different quantities, and also the whole around the world via that is International Committee for Weights and Measures, that's Mutual Recognition Arrangements, CIPM MRA. The TCRI actively seeks to build the measurement capabilities of members wishing to improve their services. So basically, if someone has to improve their capabilities, measurement capabilities, definitely that through TCRI we can get assistance and more results can be improved. The committee also conducts technical meetings and laboratory tours and manages the communications with the CIPM, CCRI, and other regional metrology organizations. So coming to radiation metrology in India, the BARC will come to specifically to the radiation standard section. The BARC is the National Metrology Institute for Ionizing Radiation. It is a designated institute by BIPM. So we had got the notification in BIPM in July 2003. Then it is also a secondary standard dosimetry laboratory, which is IAEA, International Atomic Energy Agency, have got different secondary standard dosimetry laboratories for main medical applications. So we are one of the SSDLs, and we are also collaborating with World Health Organization as a center for radiation dosimetry. So this is the BARC, basically is the apex laboratory in the ionizing radiation metrology, and our responsibility is to develop, establish, maintain, and upgrade ionizing radiation measurement standards. Primary standards, secondary standards, then reference standards for X-rays, beta, and gamma rays. So this slide shows the mainly what I had just mentioned. So this gives an elaboration of that Apex Laboratory radiation standards. We have a radiation standard section in Radiation Safety Systems Division of BARC. That particular section is solely dedicated for ionizing radiation measurements in the country, and it develops all the various types of ionizing radiation standards, measurements of X-rays, beta, and gamma, also neutron. Then it provides traceability for radiation measurements in the country through all these standards. Then the radiation standard section is the national custodian of ionizing radiation standards. So all the ionizing radiation standards are available with RSS, that is radiation standard section. And of course, I have already mentioned it is recognizes the DI, and then RSS plays a pivotal role in ensuring accurate radiological measurements in the country. Any measurement in the country is being traceable to this particular radiation standard section. And the radiation standard section is linked through various programs with international bodies like BIPM, APMP, and IEEA. This shows the hierarchy of traceability. Traceability chain, basically we have to have complete unbroken chain of traceability. So right from starting from SI standards, so we have, as I mentioned, Gray and Sievert I have mentioned, and Becquerel. Becquerel is the activity. So it is disintegration per second. One disintegration per second is Becquerel. Any radioactive element which is disintegrating, so the activity is measured in terms of Becquerel. So these are the three derived ionizing radiation SI units: Becquerel, Gray, and Sievert. Gray and Sievert I have already explained, and Becquerel just now I have given a mention that it is a unit of radioactivity. Then we have primary standard laboratories, PSDLs. Then we have SSDLs, that is secondary standard laboratories by IAEA. And under that, we have accredited dosimetry labs which can provide measurement and calibration. And then different lots of radiation users, as I mentioned, in different fields: nuclear industries, health, medicine, food, agriculture, and defense and research. So basically, radiation standard section provides traceability of radiation measurement in the country and linked to other NMIs through intercomparison programs of APMP, BIPM, and IEE. The activities of radiation standards are divided into 5 major groups. So I'll be explaining the groups one by one in this presentation. First of all is the protection level standards. That means we have lots of radiation monitoring instruments are being used for protection. For example, anyone carrying out X-ray, he has to have a radiation dosimeter. All this can be the protection level equipment. So they are mainly for the beta, gamma, and X-rays and radiation surveymeters, area gamma monitors. Any radiation facility where you are using, you have to have installed area gamma monitors so that all the time the radiation level is being monitored, and if any uh, increase in the radiation level, we get an alarm so that the corrective action can be taken immediately. So this is a mandatory requirement to have all the radiation facilities to be fitted with area gamma monitors, and of course personal dosimetry. Then coming to neutron applications, we have neutron standards group, which mainly deals with the characterization and calibration of neutron detectors and neutron sources. I'll be having one or two slides on all these activities of these particular groups, for the benefit of all of you. Then we are also have another group which is dealing with radionuclide standards group. That means anyone using a radionuclide. For example, I give an example of iodine 131 is being used as a therapy for thyroid cancers. So what whether that is a standard, the dose given is a standard dose, is a correct dose. For that we have to maintain all these radionuclide standards. So national standards for radioactivity measurement is maintained, and we establish an equivalence with international standards by participation in the intercomparisons. Then we carry out one national audit for activity measurements for radium of pharmaceuticals used in nuclear medicine centers. The nuclear medicine centers, those who use the radioactivity, so whether they have their own measurements, whether their measurements is accurate, or if there is any deviation, that we carry out a national audit for all the nuclear medicine centers. They participate actively, and they take guidance, and they say that their readings are different. If they're different, why, all we analyze, and then we give it correct. Basically this idea is to provide the accurate dose quantity of radioactivity to the patients, as well as any other matter there. Then we have radiological standards, where we have standards for therapy level dosimetry, then thermoluminescence dosimetry, postal dose quality. Many any facilities using radiation, they have to use the TLDs, that is thermoluminescent dosimeters, for their personal monitoring or individual monitoring. So that has to be a quality audit has to be carried out. So this particular radiological standards group provides that quality audit. And then coming to the chemical dosimetry standards group. So we have a chemical dosimetry standards group, which is mainly for the radiation processing applications like food processing. Then suppose we have to irradiate some like the mangoes, the example what I had given, to a particular dose, whether that mangoes have received that much dose uniformly. So we have chemical dosimetry labs, the chemical dosimeters available, which produces, which gives the accurate measurement of this dose. Generally, these chemical dosimetries are used applications used in a high dose range facility. So like dosimetry for high dose irradiation facilities. Now coming to activities in the protection level, as I mentioned, we have lots of protection level equipment which is used for different applications. So to develop and maintain various protection level gamma measuring standards, then calibration of gamma, that is there are different ranges, gamma monitoring low range as well as high range dosimeters, and then for X-ray radiation monitoring instruments like radiation surveymeters, area gamma monitors, and pocket dosimeters. So pocket dosimeters are similar to the they are personal monitoring devices which can give you the instant reading how much dose you have uh, consumed while carrying out a particular task. So this gives an instant reading of that type of dosimeters. So these all dosimeters are being calibrated in the protection level standards group. Then measurement of attenuation ratios or factors of various shielding materials. So many people will be developing shielding materials. So we provide how much attenuation, what are the factors they are offering by that shielding material. And any radiation facility, when you establish, you have to have all the radiation mapping, and then the walls and other parts have to be designed and constructed as per the requirements of attenuation, so that the public is not exposed to any higher level of radiation. So these type of attenuation ratios or factors for various shielding materials are being carried out in this protection level standards group. Then we have on-site standardization of gamma reference radiation fields and technical help. There are some labs which are using gamma radiation fields. So that has to be calibrated. So those facilities cannot be brought to the laboratory. So we have to go there for on-site standardization. Then another aspect is type testing. Lots of developments are being carried out in radiation monitoring instruments. So people are developing radiation monitors like survey meters, area gamma monitors, pocket dosimeters of different designs and different type of detectors. So entire type testing of these monitors, whosoever develops this instrument, so type testing can be carried out in the radiation standards lab here for all the ranges and as well as all the other aspects. So this is very important because type testing can cover the entire range and can give you the exact results. Then only it can go for manufacturing of the equipment. Then gamma and X-ray irradiation to various active and passive dosimeters. So all those dosimeters, if you want to calibrate, it can be exposed to radiation, and then we can read out whether the dosimeters are functioning properly or not. And of course, we participate in the international intercomparison and all quality audits. These are some of the handheld radiation monitors. Many of you may be familiar with these. So there are different types, different purposes. Some are giving you the gamma dose, as well as some will be giving you the other beta dose. Also, it can give all those type of equipments are being used in various fields. So all these type of equipments, around 400 plus monitors, are calibrated every year in the standard laboratories. Then to come to the facilities of protection level instruments, so we have a radiography camera based irradiation facility for different radionuclides like cesium-137, cobalt-60, and americium-241. And we have an X-ray machine for protection level dosimetry. And we have ISO 40371, the narrow series beam qualities for energy response characterization of various radiation monitors. Basically, the radiation monitors, not only you have to have the reading, you have to have the characterization for different energies. Generally, gamma energies will be varying from around 100 to 200 keV to it goes up to 2.5 to 2.6 MeVs. So entire range we have to cater to for carrying out the calibration. Then there is a graphite ionization chamber which is available as a reference standard. So this is the reference standard which is available as a protection level for calibration of protection level equipment. The source output of all health physics units, all the health physics units in the country. These health physics units are mainly in the reactors, the nuclear power plants. They look after the safety of the working environment as well as personnel. So their source output is being provide traceability using this reference standards. And TLD unit and calibration laboratories of the entire country is also traceable against this. So basically, this is the main reference standard which is used for all the measurements for protection level equipments. Then we have secondary standards which is 0.3 cc as well as 30 cc and 1000 cc of ionization chambers. Then we have one multi-source exposure unit having 6 cesium-137 sources and one each of cobalt-60 and americium-41. So we need to have different radiation sources because of different energies. Like cesium-137 is having energy of 662 keV, whereas cobalt-60 is having two energies, 1172 and 1332 keVs. So these are the different energy ranges, as well as activities also will be different to give different types of dose rates. Then we have sealed gamma sources and beta sources activities measurement. And as well as there is irradiation to calibrate the irradiation facility. We have a gamma pulse source which can produce high gamma radiation dose at a very short duration. These are the photographs of the equipment and then calibration facilities and the calibration setups which are available in the lab. So basically, some of you who may be interested in visiting, probably then you can have a better look of this. These are only the photographs, and this one is a calibration setup for high range instruments. This instrument which is being calibrated here is an airborne Indian environmental radiation monitoring network. These are solar powered standalone radiation monitors. Around 550 of them are being installed at various locations in the country to continuously monitor the ambient radiation level. So they have different ranges of detectors. So to calibrate high range of detectors, we require this type of facilities. So this is given one example. I have given how the calibration is being carried out. Then current practices in metrology for radiation protection in India. So we have radiation monitors for, as I mentioned, area. That means any radiation facility, you have to have area monitoring. So that area has to be continuously monitored, whether if there is any elevated level or not. And then individual monitoring, how much dose being received by the person who are working in the radiation environment. So area monitoring is normally carried out for different dose rates. So based on the exam applications, so we have different dose rates. That is, I have given 10 microgray per hour to 10 gray per hour. This is the range where we are working. And then individual monitoring is carried out by this TLD, thermoluminescence dosimeter, as I have mentioned, or some pocket dosimeters, which is worn by the person, and then it records the radiation. These monitors are calibrated using the cesium and cobalt sources as per the IEC standards, and then their output is standard using the ionization chambers. So these are some of the equipment which is shown as fixed radiation monitors as well as handheld, then electronic pocket dosimeters, and then standard ionization chambers. To carry out calibration, BRC has developed accreditation is given by NABL, and BRC has helped in setting up calibration laboratories at different locations. IGCAR, Indira Gandhi Center for Atomic Research, that is a part of DAE, and ECIL, Electronic Corporation of India Limited. These are the two, and then BRIT, Board of Radiation and Isotope Technology. These three technologies are of they are of Department of Atomic Energy, whereas other labs like PLA, Nuvia, these are private labs. So BRC is help them in establishing the calibration facilities as well as providing the traceabilities. This is a simple map, shows it is located at different places. The previous slide, which are the locations it is showing in this particular map. Now I have done with the protection level standards, then coming to neutron standards, which is used for characterization and calibration of neutron detectors and neutron sources. So activities of neutron measurements is development, establishment, and maintaining national standards for neutron sources. So we have in our reactors, so the neutron is one of the most important parameter which is to be measured on power neutron measurement in the reactors. So we are producing, we are giving the solution for neutron measurements in the reactor. Then calibration of neutron survey meters, and all those location places where neutron survey meters are being used, they are being calibrated here, and different neutron flux monitors. Then of course we have testing and calibration of startup channel. So when reactor starts, we have to have different levels of monitoring, like fission chambers, and then also we have some new failed fuel detection system, which is based on the neutron measurement in the nuclear power plants. Then on-site absolute measurement of thermal and fast neutrons. Thermal neutrons are which is having energies lesser than lesser, and whereas fast energies are having higher energy. Then measurement of neutron spectrum. So the entire neutron spectrum can be measured, and the dose rate can be evaluated. How much dose is being received by that particular neutron field or neutron source. And of course, measurement of attenuation, like in protection level, we had attenuation for gamma. Here we have measurement of attenuation for neutrons. We have different shielding materials for neutron. For neutron, generally for gamma, we have lead as the or high jet material as the shielding material, different types of materials. Whereas for neutrons, we need hydrogenous material so that hydrogen absorbs one neutron, and so that is why HDP or any hydrogenous based paraffin, all those are the very good shielding materials for neutrons, including concrete. Then facilities, we have a standard thermal neutron flux facility. So here we are able to produce what type of thermal neutron flux is required. Then we have a neutron source identifier. We can identify the neutron source as what energy. Then we have standards for neutron source yield measurement, that is manganese sulfate bath, which is the primary standard. Then there is a precision long counter, which is a secondary standard. And we have recoil proton neutron telescope for 14.1 MeV neutron measurement. So it's a very high energy. Then 4 pi beta gamma coincidence counting system, and high purity germanium based system for activity measurement. Then activation foils. So some neutrons as some of the places where a neutron field is very high, they are inaccessible. So what can be done is neutron foils can be placed in that area, and then after activation, with through fast and thermal neutrons, the activation products, the activation, how much activation has come, that can be measured, and then we can find out the neutron flux or neutron field. Neutron spectrometers, there are some neutron spectrometers that are also available, and then portable transfer standard for laboratory neutron sources. These are photographs of manganese sulfate bath, the first one, and then we have the REM counter calibration facility. This is the REM counter, which is widely used for neutron measurements. Then we have neutron multispectral assembly, then portable PLC, then thermal neutron facility. This is here we are getting the thermal neutrons of different energies. Then we have the precision long counter. And another aspects are that Bonner pairs, then any 213 based neutron spectrometers, then bubble detectors based neutron spectrometers are available, and then threshold detectors. This is one of the new addition to our facility, which is an automated neutron calibration facility. Here we have a robotic arm, as well as this is the robotic arm, and as well as a neutron storage facility with shielding. So we can program, and this particular robotic arm can pick up the particular source and bring and keep it in a stand through which we can calibrate the neutron radiation monitors. So this completes protection level standards and neutron standards. Then coming back to radionuclide standards, which maintain national standards for radioactivity measurement. So all the radioactivity measurement is being addressable to this particular group, radionuclide standards group. Then establishment of equivalence with the international standards and national audit. As I had mentioned, we are carrying national audit for nuclear medicine centers. So the activities of radionuclide standards groups are development and establishment and maintaining national standards for radioactivity measurement, and establish equivalence with international standards by participating in inter-comparison programs of BIPM, APMP, IAEA. The organized national audit for activity measurement for radiopharmaceuticals used in nuclear medicine as a part of quality assurance program for nuclear medicine centers of the country. Then we have a standardization of radioactive sources, both in the solid and liquid form. Then provide a standard reference radioactive sources to various users in DAE, then industry, hospitals, and defense. Then the radionuclide standards groups also carries out calibration of dose calibrators. In the nuclear medicine centers, they use radionuclide calibrators. So then those calibrators has to be calibrated frequently, and we are producing the calibration traceability for the nuclear medicine centers. The facilities of radionuclide standards are a proportional counter-based 4-pi beta gamma coincidence system, then 4-pi liquid scintillation based beta gamma with sodium iodide thallium activated coincidence counting system, then automated liquid scintillation scintillator based coincidence system. These all three are basically measuring the radioactivity, but they're using different techniques so that we can establish the primary standards. Then of course we have the large area multiple wire proportional counting system. And for secondary standards, we have HPG, that is high purity germanium detector, that gives a very high resolution spectrometer, the spectrometer result of the materials which is being monitored. And there is an well type re-entrant high pressure gamma ionization chamber. These are the photographs of the facilities. As I said, that liquid scintillation is 4-pi beta gamma coincidence system. Then we have proportional counter based 4-pi beta gamma systems as well as automated liquid. These all three measures the same quantity but with using different principles. So this gives us reduces the uncertainty in the measurement significantly. Then another, we have large area multi wire proportional counting setup. Then well type high pressure ion chamber, graphite ion chamber, and then HPG high purity germanium detector. And these are the comparison of all national audits results. So we started way back in 1979, and then as you can see, gradually these are being increased. The most important part here is most of the center calibrators are less than 10% deviation, which is very well accepted all over the world. And then there are a few are slightly more than 10% deviation, whereas they can be then we are producing them the solutions to bring their deviations less than 10%. So this completes radionuclide standards. Then I have got two more standards group, radiological standards group. So they are having the standards for therapy level dosimetry. So wherever this therapy dosimetry is used, then a thermal elimination dosimetry postal quality audit. So their group, they are also having participation in international integration programs for air karma as an absolute standard to water measurement, and then international traceability provided to radiotherapy centers by calibrating their dosimeters in the telecobalt unit. So this is as per IAEA TRS 398 protocol. Then calibration of well type chambers for iridium 192, then cesium 137, and cobalt 60 brachytherapy sources. Brachytherapy sources are used, which is implanted in the near the affected organ, and so they continuously keep on giving the dose to get the cancerous cell cured. So these are implant based brachytherapy is the implant based sources. So it is implanted into the body. Then calibration of beta radiation monitors and detectors in terms of H-07, that is skin dose as per ISO 6980. Then calibration of instruments using diagnostic radiology as per the protocol of IAEA TRS 457. Then the radiological standard group also carries out dosimetry quality audit programs for thermoluminescent dosimetry postal quality audit under reference conditions. Here, what is generally done is a particular different type of dose is exposed to the TLDs, and then it has been asked to the different facilities, they read out the doses and we carry out the intercomparison. And also IMRT quality audit is being carried out, that is intensity modulated radiotherapy. These are the standards available with the radiological standards group. This is a table, radiological quantity, that is secondary standard for cylindrical ionization chamber. The beam quality is cobalt 60 and it is with BIPM and APMP intercomparison. Then similarly for primary standards and free air ion chambers, we carry out for X-rays and APMP intercomparison. Then a reference standard for cylindrical graphite wall chamber, that is for iridium 130, 192 and cesium 137. These are the BRC reference standards, and reference standards for extrapolation ion chamber, that is strontium 90, yttrium 90, and then krypton 85, that is BRC standards. The facilities what we have in radiological standards groups are a Theratron 780E telecobalt unit, which is 6,500 curies as on last measured was in 2018. So cobalt is having a half-life of 5.6 years. So it decays. So that is why we have to have the measurement of the activity as of on regular basis. Then there is a Gylon X-ray machine, which is producing 15 to 320 kV. And brachytherapy, HDR brachytherapy source moment system, it is for iridium 192, and beta calibration facility for strontium 90, tritium 90, and krypton 85. Traceability of dosimeters in external beams is being produced. This is the telecobalt machine which I was mentioning, and I had mentioned regarding the calibration of Hermon also, the same system was used. And then you have a cylindrical ionization chamber and a plain parallel chamber calibrated at SSDL BARC. And these are the reference standard ionization chambers traceable to BIPM. So around 300 plus chambers are calibrated every year using this facility. This is one typical certificate which shows IEEA TLD audit for SSDLs. So we have a deviation is minus 0.07. So it is a very well accepted result. So this was carried out in 2021. Then reference air karma rate calibration. These are the facility for air karma rate calibration of iridium 192 and cobalt 60. So around 120 well type chambers are calibrated every year. So they are being used in the high dose rate cobalt 60 sources. Diagnostics, X-ray and radiation standards. X-ray diagnostic, the X-ray diagnostic calibration facility is shown here. So these are the photograph of that X-ray diagnostic calibration facility. Now coming to the last group, that is chemical dosimetry standards group, which is mainly for the radiation processing applications and radiation therapy. They uses chemical dosimeters for high dose irradiation facilities. The activities of chemical dosimetry group are development, again, establishment of chemical dosimetry standards for therapy and processing, maintaining national chemical dosimetry standards for high doses, that is comes in the range of kilogray. Calibration of high dose radiations. So any radiator facility using high radiation field, high dose radiation field, their dosimeters have to be calibrated. So we produce this particular group gives the calibration facilities. Then carrying out a dose assurance program for radiation processing plants. For example, a particular plant is giving X amount of dose, whether they are giving it correctly or not. So there is assurance programs are being carried out to give them confidence that they are doing it in the correct way and the correct dose is being delivered. And of course, they perform chemical dosimetry for special applications, and then calibration of gamma chamber 900 using a freaky dosimeter system that is as per ASTM standard EI 026 2003. Then low dose dosimetry, for example, blood irradiator dosimetry. So that is also used in blood irradiator dosimetry, and development of dosimeters and radiation indicators for radiation processing applications. These are the chemical dosimeters which is available. Gamma chamber board of radiation and isotope technology. They produce GC 900 and 1200. So we are giving the chemical dosimeters for these particular chambers. Then chemical dosimeters like Freaky, Seric, Cirrus. Then in-house and indigenously developed dosimeters. Different type of dosimeters are being developed. And alanine in EPR spectrometry, that is alanine is used for grain irradiators, where how much dose is being delivered to the grains. So that these type of dosimeters are being used in that. Then there are spectrometers which are available in UV and near UV IR ranges. We have one semi microanalytic weighing balance that is exactly required for preparing the dosimeters. Then, of course, fume hood facility is required for corrosive chemical materials to be used, and then convection oven. These are the photographs of chemical dosimeters as well as chemical dosimetering systems. So these are the chemical, basically the chemical dosimeters. Once they are exposed, the color of that dosimeter, that particular chemical changes, and from that we can find out using the UV and NIR spectrometer, we can find out how much dose is being received. We have the calibration for the non-exposed doses. And this is the applications of chemical dosimetry in all the fields where you are using high radiation dose. The chemical dosimetry is used. So we have the radiotherapy there also it is used, and blood irradiation and medical sterilization. Many of the medical equipment have to be sterilized using radiation, high radiation field. So there we are using calorimetry. Another application which is sludge treatment using radiation sources. So this is being used in many facilities, many sludge hygienization facilities. The radiation sources being used there also, exactly what is the delivery of dose that is given by the chemical dosimetry. And of course, in the food processing, as I said, mango irradiation as well as other spices, and even for meat and fish products, there also it is being used. So to summarize, that radiation services is being given to the nuclear reactors, then all the applications in the hospitals, then industries wherever the radiation is used, R&D labs, the accelerators. The accelerators are the alternate technologies, and then in defense. That means the radiation standard section of RSSD, radiation standards safety systems division, BARC, provides radiation services and traceability to the measurements in all the fields which are used in our country. So with this, I'd like to conclude my presentation. Thank you.
Thank you very much, sir, for your brief and very interesting and the important explanation of this radiation metrology. Really, we are thankful to you. Atulji?
Yes, sir.
Ronak, kindly I will request all the participants to kindly switch on your mic and switch on your videos so that we can take the pictures. We have with us our Honorable former Director of Legal Metrology, Government of India, Shri B.N. Dikshit Sahab. Sir, you are here?
Yes, yes.
Thank you very much, sir. Actually, sir, today we have a very important topic related with the radiation metrology. The expert, Professor Chaudhary, was from Bhabha Atomic Research Center, who is a known scientist in this field. As far we are all aware, National Metrology Institute, National Physical Laboratory of India, National Physical Laboratory India is basically NMI for all the fields except this radiation metrology. Radiation metrology being DI, Designated Institute, Bhabha Atomic Research Center participate in BIPM and CIPM since beginning. Inside, remember, since 2000, it is doing it. So, sir, we have with us Professor Chaudhary, who has made this beautiful explanation. Sir, I would like to request you to kindly share this presentation to me. We will place this video in the on the YouTube channel, and your presentation we will share with all the participants. Thank you, sir. Sir, Dikshit sir, would you like to speak 2 words, please?
Uh, yes, Ashutosh ji. This was very nice lecture given by the Professor Chaudhary regarding the radiation of so many equipment. So one important things he told regarding the utilization of such radiation equipment and then their prevention in the hospitals and where the X-rays machines are there and photometries are there and so many things are being scanned in the hospitals. So that is the important. Another is the laboratories where the all these equipments are being used. So there the this how to save the people who are working there and the peoples who are entering to the labs, they should be restricted. There should not be harm to the people as well as to the laboratory officers who are taking the experiment due to uh, the radiation and all that very things. Radiations are very important even in the radioactivity radiations as well as the UCs that the nuclear radiations are there also there. So uh, sometimes it becomes nearly impossible that the where the radiations are going and up to what limit it is going on. So for that the scientists are doing their best work. I hope that the Professor Chaudhary lecture will be very beneficial to us and in future we will think that how much safety we should make for the laboratory purpose. Thank you, Astoji. Thank you, Professor Chaudhary, and other scientists who are participating in this very program.
Thank you very much, sir. Thank you for your kind and motivating words. Sir, I remember when I was working about 30 years back in All India Institute of Medical Sciences in the cancer hospital. So we used to use this, small type of chip to do the radiation, to do the work or test work of monitoring the radiations, how much radiations are falling on a patient during the cath operations and other treatments. So, it's a very interesting and a very good topic, and how the nuclear medicines are helping the patients for different purposes. As well as, sir, these now as we discussed, these technologies are very fruitful, very useful for increasing the lifespan of the perishable food items. So how we can develop our industry, how we can support our industry, food industry and other industries. This is a very important subject, very important parameter, sir. Certainly we will look towards Atomic Research Center to coordinate with the legal metrology wherever possible, how we can ease the life of the people, how we can help the industry for developing new technologies. If anybody wish to speak anything, you are most welcome. Thank you, sir. Otherwise, I would like to thank all the participants, Professor Chaudhary, Mr. Dikshit, sir, and rest of the participants. We will meet next week with the next topic. With this, I would like to thank all.